In this video, I'll walk you through the process of extracting some important details from a fitted linear model object in R. I'll do this using the heights.csv dataset, which came up on your second exercises this semester. So I've already clicked on the Import Dataset button in RStudio and surfed to the location of my hard drive where this file sits. Here it is, heights.csv. I'll go ahead and click Open. Inform it of all the relevant details. It seems to have understood that there's a header row that's separated by commas, etc. So everything looks all squared away up here. I'll click Import. Now I've got the heights dataset here. Let's just remember what these columns are. S, HGT is student height. M and F refer to mother and father's height. So these are some heights of UT students. I think this is the first class I ever taught at UT. Their height and the height of their mother and father in inches. Okay, so there it is. Actually, I have two copies over here. I can close both of these. Now, I've just put a few commands up here that you'll want to replicate in your own little script. Just keep in mind it's good practice when you're entering R commands to enter them into a separate script up here, which you could then save rather than enter stuff down here for the purpose of reproducibility. Okay, so obviously I'll plot my data here. Here's student height as a response variable with mother's height as a predictor variable. You can see there's a clear linear relationship here. And to do that, to express that, I'll fit a linear model using the lm function. So here it is. I just clicked on that and hit Command Enter, and now I've got my linear model object. And you should be aware now of how to do some basic things with one of these guys. So, for example, I could feed that lm1 object that I've stored here into the AB line command and get the fitted line superimposed upon my plot. You may recall that we can also do things like extract the coefficients of the model, that is the slope and the intercept. So here I'll put my cursor on that line, hit Command Enter, and I get the intercept and the slope associated with the predictor variable, MHGT here. I can also, if I want to spit out the residuals or the fitted values of the regression model on my computer screen, I can just highlight those, hit Command Enter. There's the residuals, there's the fitted values. Now that's of limited utility to just get them spat out to the screen. It's more useful to do things with them, either store them in a secondary object, which I could do, maybe call this F's equals resid and, Y hat equals fitted of lm1. Now you notice those don't return anything, rather they store their results in these F's and Y hat vectors. I can also nest functions in R, so resid of lm1 returns a whole vector of residuals, so it is fitted of lm1. And notice I feed that vector into the SD command, nesting these functions here. I get the standard deviation of the residuals and the standard deviation of the fitted values, which could be useful for verifying the fact that we know about linear models, which is that the standard deviations of the fitted values, the residuals, and the original values, the y values, that is, form a Pythagorean triple. All right, now if you wanted to, for example, add another line to the plot, say to plot the boundaries of a prediction interval, let's just say I wanted to, instead of the line associated with the best fit here, which would be the line having intercept 32.8 and slope 0.57 and a bit. Let's say I wanted to add a line with intercept 35, so 2 units and a bit up, and this with roughly the same slope. Well, the AB line is a function that's overloaded in R. You can feed it multiple things, and it'll interpret different arguments in different ways. So up here, if I feed it a linear model object, it'll plot that line of best fit. But if I feed it 2 numbers, it interprets those numbers as an intercept and a slope, and it'll also plot that line on the active plotting window. So you notice if I put my cursor on that line and I hit Command Enter, I get a different line superimposed. And you notice it's kind of shifted up. It's got roughly the same slope to 3 decimal places and a different intercept. That should be useful if you want to plot the boundaries of a prediction interval. I leave it to you to figure out what the slope and intercept of that line should be. Another thing you can do by feeding an LM object with function is to extract R squared. So the easiest way that I know how to do that is using the summary command, but I'm not going to get to that just yet. I'm going to first show you how to do it with the ANOVA command. So ANOVA, A-N-O-V-A, stands for Analysis of Variance, breaking down sums of squares. It's pretty obvious what happens here. We're going to get the sums of squares associated with the fitted values and with the residuals. And we know from the variance decomposition, TV equals PV plus UV, that's our PV right there. That's our UV, and the sum of those two sets of sums of squares is going to be TV, or total variation. So from these two numbers right here, you could very easily calculate just here in the cursor window in R what R squared would be. Now, it's also returned R squared, that is, by the summary function, and I'll show you where it is. this thing called multiple r squared and adjusted r squared. Don't worry about anything else on this screen right now except for multiple r squared. This is a bit of a misnomer because it's only single r squared in this case, but we'll get used to in the long run looking at this summary function quite a lot. But I've sort of shied away from calling this function yet because it returns a lot of information that we haven't learned how to interpret yet, and I'd rather get you sort of used to understanding r squared as a ratio of sums of squares rather than as a magic summary that pops out of the regression output. So there it is. I would encourage you to at least once or twice hand calculate it from the ANOVA table here rather than jump straight to the summary command.